Hi everyone, today we are at our seminar hosting Guido from Rutgers University. Guido, please start.
All right, thank you very much for having me. Today I'm going to talk about optimal maximum load on dynamic balls and bins. And this is joint work with this very beautiful group of people. So this talk is divided into two parts. On the first part, I'm going to talk about balls and bins games. And more specifically, I'm going to show you how we solved a long-standing open problem. Then we are going to apply the theory we developed in this part. And I'm going to show you how to develop a new type of hash table that we call Iceberg hashing. And in particular, this hash table achieves optimal times and optimal space, and it does not do any kind of cuckooing or reallocation of the elements. All right, so let me start with balls and bins game. So I know most of you are familiar with balls and bins, so this will be mostly a warm-up, this first part, the beginning of the first part of the talk. But I hope it helps. So in the balls and bins games, we have n balls and we have n bins, and we throw balls into the bins according to some rule. And once we have thrown all the balls into the bins, we ask some question like, what is the max load of any bin? Or how many empty bins do we have? Or how many ball collisions do we have? In particular, in this talk, I'm going to focus on the first question, the max load of a bin, which is the maximum number of balls you can find in any bin. OK, so how do we throw balls into bins? So the most simple way to do this is with this algorithm called single, which is you choose a bin at random and you put the ball there. So for instance, if you have these bins and those balls distributed into the bins, you select a bin at random, let's say 6, and you place the ball there. And so for m equals n, the max load is going to be roughly log n over log n. This was shown by Gonnet in 1981. Now, if we, instead of just choosing one bin, we choose d bins at random, or d larger than 1, and we select the one with the least load, we get greedy d. And so, for instance, let's say we want to do greedy 4. We select 4 bins at random. And from this bins, the least load is at bin 4. So we place the ball there. And the max load in this case drops exponentially to log n divided by log d plus a constant. And this was shown by Sar, Broder, Carlin, Ufal in 1994. And this is a very nice and clean algorithm, and it would seem that this is optimal. And it's very symmetric. So the next algorithm completely breaks that symmetry. This is left d, and this is a longer one, so let me break it up. First, we're going to partition the bins into d groups of roughly the same size, n over d. So let's say we want to do left 4. And then we're going to choose a bin at random from each group, and we're going to select the one with the least load. So for instance, we pick 1, 3, 5. Sorry, it's a bit laggy, and 8. And from these bins, you see that 5 and 8 have the minimum load too. And so finally, we break ties choosing the leftmost bin with the least load. So in this case, we choose 5. And in a very shocking result, Vakin showed that the max load is now log n divided by d log phi of d plus a constant. And this log phi of d is just a constant between 0.47 and 0.7. So the important thing here is the d in the denominator. So what this means is that the max load drops exponentially as a function of d. Okay, so we have these 3 ball allocation rules. What about other rules? Well, there are.
Can I ask a question for the previous slide?
Please.
What is the range of D? I mean, how large D can be for it to still make sense? Can I set D to be log n or log n in the first or in the second case?
Right. So when D is log n, you're going to get max load 1, right? That's what it claims.
Yes. So that's my question. If I set D to be log n in the second case, do I get a constant load?
Yes. If it's log n, then you already get max load constant. Yes. Yeah. There's no constraint on D.
Okay. Thanks.
Okay. So there are many other good ball allocation algorithms, but we are gonna focus only on these 3 because they are online, which means that they place a ball before seeing the next one. They don't reallocate balls, meaning that when you insert a ball, they don't move other balls around. And they use a tunable number of bin choices D. So this was, you sort of read my mind, Professor Mac. This is what you can do with these algorithms. You can choose D as small or as large as you want. And what the guarantee you get is that the work you're gonna do on each insertion is D. And finally, we have a lower bound, which is that lefty's optimal has optimal max load up to low order terms among all online algorithms that use D choices per ball, no matter how you generate those D choices or how you break ties. And this was shown by Vakin in the paper he introduced lefty.
A question?
Yes.
What do you mean online? Is there normally the idea in online is that you don't know something about the future? What don't you know?
For instance, if I gave you all the balls in advance and you could select, you could arrange them on the bins arbitrarily, that would be offline, right? But now you get 1 ball at a time and you have to place it on a bin before seeing the next one.
But the balls are all the same, right? So if you know how many balls will arrive, for example, then you could do exactly the same. And even if you don't, if you are allowed to count, then you could just, or to remember where you put it, you put 1 in the first, 1 in the second, right? Normally, this captures the case that you cannot do that for some reason.
Yeah.
But
yes, so this restriction of online makes more sense when you have a dynamic system. When assigning sequentially, for instance, is just not optimal. And so, and you don't have all your requests. So for instance, suppose you have a load balancing system where you get a bunch of requests. And some of those machines will finish you send requests to machines, right? And some of those machines will finish their work earlier than others, right? So you can't just go.
So some balls disappear also.
Yes, exactly. So yes, so this restriction of being online makes more sense when you have a dynamic system. Okay, so all right, so the max loads we saw were for m equals n. So what about m larger than n? So I'm going to define this value h, which is the average load, and I'm going to use this for the rest of the talk. And the observation here is that the max load cannot be below h, right? The max has to be at least the average. So really, you should think of all of these max loads as h plus some deviation from this absolute optimal h. And so what are the max loads for these three algorithms? I'm going to divide this table into 3 regimes, depending on h being much lower than log n, roughly log n, or much larger than log n. So single has these max loads. And the important thing here is that on the first two cases, the max load depends asymptotically on h. But in the third one, it's exactly h plus the deviation, right? So the deviation in the third one is really, really small. It's a little low of h factor. This was shown by Rob and Steger. Then moving on, greedy has max load, which is the same we saw before in the case m equals n, but now we have this h term. And again, you can see that this is an exact dependence on h, plus the deviation, which is log n over log d plus a constant. And this was by Bernbring, Chmai, Steger, and Bocking. And for lefty, the max load is, once again, the same max load as we saw before, plus an h term. And this was in the same paper, Bernbring, Chmai, Steger, and Bocking. Okay, so we can say two things from this chart. First, that lefty is better than the other algorithms in the three cases. The other thing is that most of these max loads are already optimal up to low order terms. So for instance, let's focus on the lower left corner. That is, as I mentioned, that is h plus little low of h. And so the same happens for greedy. These are all h plus little low of h, except the first row where this is only true when h is sufficiently large. And for lefty, we get the same with the same expression. This is all h plus little low of h. Okay, so you have a pretty good understanding of what's the max load for these algorithms in any case. Okay, so all of these results are when only insertions are allowed. So what about when you have a dynamic system where balls can not only be inserted, they can also be deleted and reinserted in an arbitrary fashion? So let me be more specific. Each ball has an ID, and bin choices are computed via hash functions on that ID. And so this has an important implication, which is preservation of choices, which means that when a ball is reinserted, the random choices are the same as before. So the first time you see a ball, the choices are random, but then the second time, the third time, and so on, there's no randomness. And an important remark is that now we're going to treat m as an upper bound on the number of balls in the system at all times. It's not the exact number of balls we throw into the system, right? We can throw in balls, delete all of them, throw another m balls, and so on and so forth. Okay, and we are always going to consider oblivious adversaries, which means that the sequence of insertions, deletions, and reinsertions are generated without knowledge of the random choices. And the adversary cannot learn the random choices as well. Because if he can learn the randomness, then he can always select a group of balls that choose the same group of bins. And so he can force a distribution where balls are concentrated in few bins. Okay, so let me give you a bit of the big picture of all of these settings that you can attempt when you're working with balls and bins. So when I was a kid, I used to play Mortal Kombat a lot. I don't know if you know what Mortal Kombat is. If you know, it's a fighting game where you choose your fighter, or at least in the first version I played, you chose your fighter, and then there was a voice saying, "Choose your destiny." And you had to choose one of these towers with a lot of fighters. And so you started fighting against the fighters at the bottom, and you made your way up until the big boss, and the difficulty was growing exponentially. Like the very first fighters, they almost let you beat them, but then the big boss was just impossible. And so balls and bins games are somewhat like Mortal Kombat or the game of your choice. At the base, you have proving bounds for single, and in any kind of setting. And here you only need basic probabilistic tools. Then you have greedy D when m equals n, but you don't have deletions. And this was a 5-page long proof using a technique called layered induction. So it's not terribly hard. Then you have greedy D when m equals n, and you have deletions, but you don't have reinsertions. And this was shown in a paper by Cole, Max, Mitsumacher, Richa, Sitaraman, Upfal, and they used a technique called witness trees. And now it starts getting really, really, really challenging. So here you have proving bounds either for greedy D or left D when m is larger than n and you don't have deletions. And this was a 36-page proof using heavy markup chain machinery and lots of calculations. And at the very top of the tower, you have greedy D or left D when m is larger than n and you have deletions and reinsertions. And this was only attempted in a paper by Vakin, where he also used witness trees. But the thing with this paper is that the bounds are weak. So what do I mean by weak bounds? Well, let's go back to the table, and now let's fill it up with the max loads for the dynamic case. So single is going to have the same max loads. And this is because single is history independent. And I'm going to talk about that in a bit. But for now, you should think that in single, when you insert and delete a ball, it's the same as that ball really never existed. Now, the max loads for greedy are almost the same as before, except that now the dependency on H is not exact. We have an O of H. And for lefty, we have the same thing. Now it depends on O of H instead of exactly H. And so the consequence is that now all of these max loads are O of H, except for the first row, that's only true for large H. And the same thing happens for lefty. So now all of these max loads are not optimal up to lower order terms. Right, they're far from optimal. Okay, any questions so far? Okay. So the open problem is to design a ball allocation algorithm with max load H plus log n divided by D log phi of D plus lower order terms with high probability in the dynamic game against an oblivious adversary. So this means that when H is larger than log, then this is going to be optimal up to lower order terms. Then when H is smaller than log, it's going to have the same max load as lefty up to lower order terms. Okay, and this has been an open problem for almost 20 years now. And in fact, in a personal communication with Petra Bernbrink, which is one of the authors in this 35-page proof of balls and bins, she told us that this is actually an open problem that people really cared about. Okay, so let me argue why this is hard. And for this, I'm going to introduce this concept of history independence. We say that a ball allocation algorithm is history independent if the outcome of every time step t is only a function of the set of balls present at that time. So in particular, this means that the analysis is not a function of the sequence of insertions and deletions leading to that point in time. So single is history independent because when you insert a ball in single, that selection does not depend on the state of the system. But on the other hand, greedy and lefty are not history independent because their selections depend on the loads of the different bins. And therefore, history-dependent algorithms force us to look at the sequence of operations leading to some point. And when you combine this history dependence with this phenomenon of preservation of choices, this is poopy. This is just too hard to manage. Okay, so in our work, we solve this open problem. We design an online ball-allocation algorithm that we call Iceberg D that uses D+1 choices per ball. And the theorem is that at any fixed time step, the max load of Iceberg is at most h plus log n divided by d log phi of t plus lower order terms with higher probability. Okay, so how do we achieve this? Well, we exploit the following trade-off. Single is history independent, but it has, so it's easy to analyze, but it has large max load for most values of h. Lefty is not history independent, but it has provably small max load when there are not too many balls. Say h is a constant. And let me remind you, this is the max load for lefty. So when the O of h term is constant, then this is within the bounds we want to achieve. And so what we do in Iceberg D is we use single for most balls, but then when the max load is growing too large, we're going to use lefty for those balls at the top, so the max load doesn't grow too much. Okay, so let me describe exactly what Iceberg D is. So let me introduce a couple of definitions. We're going to label balls as level 1, level 2, or level 3. And the label and the bin selection will depend on some thresholds. At level 1, every bin will hold at most tau balls, where tau is h plus little of h. At level 2, we have that in aggregate there can be at most phi balls, where phi is O of n. And at level 3, there is no restriction. You can place as many balls as you want. Okay, so let me show you a picture of this. You suppose you have this 8 bins, and your threshold tau is there, and you're going to have some balls in level 1, and level 1 has at most tau balls, so that's a per bin threshold. Then you're going to have some balls in the second level, and the threshold here is an aggregate one. So at most, in total, you have at most phi balls. And finally, you have some balls in level 3. But there is no limit on them. Okay. So how do we allocate balls? First, we select a bin with single. If there are less than tau balls at level 1 in that bin, we place it there and we label it level 1. If there is not room in that bin level 1, we go to level 2 and we check if there are less than phi balls level 2 overall. And if so, we select a new bin using lefty on those balls. And if there is no room in level 2, if we have phi balls already, then the ball selects its original bin, the one we chose in step 1, and we label it level 3. Okay, so let me do a couple of examples. Suppose you have this distribution of balls, and we're going to work with d equals 4 and phi equals 21. So at this point, we have 20 balls in the second level. So let's insert a ball. First, we pick at random one bin. in this case 3, and there's room in the first level there, so we just put it there, and we are done. So let's go with another ball. We pick a random at one bin, and in this case, the first level is full, so we go to the second level. And so now we're going to do left 4. So remember, left 4 divides the bins into 4 groups, and then it selects a bin at random from each group. And so, for instance, let's say we select 2, 3, 5, and 8. And in this case, the least load is at bin 3, so we place the ball there. And now we have reached capacity, which is 21 balls. Okay, so let's go with the third ball. We pick a bin at random. The first level is full, so we go to the second level, and the second level is also full because we have 21 balls. So we just put the ball in the bin chosen by single, and we label it level 3. So that's the new green ball. Okay. Okay, so what's the intuition? Why does this work? All right, so the theorem we're claiming is that one. That's the same one I showed you before. So when h is much larger than log n, the max load of single, and I'm taking this from the charts we saw before, is h plus square root of h log n. And this is at most h plus lil of h, and this is below tau. So here we're never going to surpass the threshold tau, and so we can think that Iceberg D is just single. And by the way, this is intuition. Okay, so really the interesting case is when h is O of log n. So now the max load of single is going to be larger than tau. So some balls are going to be placed in level 2 and level 3. So the way to think this case is, forget about the levels. Suppose you throw all your balls with single, and you want to select tau. So the question is, how do you need to select tau so that the number of balls that you get above that threshold is small? And specifically, let's say it's O of n. Well, and the answer to that question is you need to select tau to be h plus little of h. And I'm not specifying the little of h here because we need that only for the calculations, but it's not really important for this intuition. And so by selecting tau the way we did, we get the following proposition, which is that at any fixed time step, number of level 2 and level 3 balls is O of n, which is smaller than phi with high probability. And this proposition is the main technical challenge of the proof. So for now, let's assume we have this proposition. Let's see how it implies the theorem. So the level 1 max load is going to be deterministically at most h plus little of h, right? Because we have this per bin threshold. Then for the level 2 max load, we're going to use the formula we know, the weak bound we know for left D. And by construction, we know that we always have at most phi balls. So we just plug in phi in that formula. And since phi is O of n, that term is really a constant. So this is within the bound we want to achieve. And finally, we claim that in level 3, we never have balls with high probability. And the reason is that level 2, by the proposition implies that that level 2 is always going to be under full. And so every time I insert a ball, it's going to go to level 2. Okay, so far so good. Okay. So what time is it? How much time?
I have one question about level 2. I mean, so my intuition tells me that, I mean, you are going to say that there are phi balls at level 2, but
Yes.
those, I mean, can we say that those were like independent? Because are there no
Oh, no. Yes.
correlations there?
There's a few of correlations. Absolutely. Yeah.
So do we have tools to actually, I mean, isn't level 2 this left D algorithm requiring that the balls inserted there were independent? What do we assume about the adversarial power in level 2?
So really, the important thing in level 2, for the proposition, it really doesn't matter what algorithm you use in level 2, right? This just says that the number of balls there is some number, but that would be true regardless of what algorithm. Really, this proposition is talking about the dynamic between level 1 and level 2. And you're true that there are a lot of correlations to it, and we are going to have to deal with them. And so that's the technical challenge when proving this proposition. Okay. So let me talk a bit about the challenges when proving this proposition. So let's say step T, and let A1 to AM prime be the set of balls present at T, right? So, and we want to prove that at that time step there are OFM balls in level 2 and level 3. So let's define Ti to be the most recent time when AI was inserted. And let's define this variable, which is the sum of these xi's, where xi is 1 if AI was placed in level 2 or level 3 at Ti. Right. And so what we want to show is that x is at most often with high probability. Okay. Oh, and so perhaps first we should note that these variables are correlated because they depend on the same randomness. That there are a lot of, they could be balls shared by all of these steps, and therefore these variables are not independent, so we can just apply Chernoff or some similar type of bound and get concentration for x. So we got to do something smarter. So the first problem we encounter when we deal with this random variables is that these xi's are history independent. So they actually need to know what the history leading to that point was. And so one trick we use, this is a very simple trick, there's nothing really deep about it, but it's really important. We need to rethrow the balls before inserting AI. And we do this rethrowing just for the sake of the analysis. We are not going to do that. We don't do that in the algorithm. Let me show you what I mean by rethrowing. So suppose this is time Ti, and you want to throw ball AI. And so this depends on what happened in the past. And so to eliminate that, we're going to just rethrow all the balls like that with the same randomness. And so now this does not depend on the past. It only depends on these balls. And and I should say here I'm only using single. I don't care about the second level. I just take all the balls and throw them with single again. And so if in the previous setting, ball AI landed in the second level, it's also going to land in the second level when I throw it in this case, after rethrowing all balls, right? And so when I do the analysis here, I'm going to get an upper bound. This is an upper bound on the variable x. And so what we really do is we bound what happens in this case when we rethrow balls. Then problem number 2 we get in the analysis is that when we, and this is related to your question, Prasad. When you insert a ball AI, you're going to have all sorts of dependencies because, for instance, you could have already inserted and deleted AI in the past, so you already know its choices. And so this is the poopy emoji problem. You get this preservation of choices, and so you lose randomness the second time you insert the ball. And so these are the really complicated dependencies to deal with. And to do this, we use a tool called McDermott's inequality. And McDermott's inequality, it's a long statement, but let me read it out loud for you. So let's see C1 to Ck be independent random variables taking values in an arbitrary domain. And let's say you have a function that takes those random variables and gives you a real number. And so now suppose that for all I and for all Ci's, if you change the ith coordinate of the function, the function only changes slightly by a term, by at most b. And this measure of the variance when we change a single coordinate, it's called Lipschitz condition. And that's the way it deals with all dependencies. It encapsulates them in this Lipschitz condition. And so now let x be f of those random variables. And the inequality claims that x is at most the expectation plus O tilde of square root of kb, where k is the number of independence you feed to McDermott's inequality, and b is the Lipschitz condition. So one thing to note here is that this inequality is only strong with the amount of independence you feed to the inequality is relatively low. All right, so this is a very powerful tool, but it's no silver bullet, because first you need to prove the Lipschitz condition holds for some b, and that b has to be not too large. And then the amount of independence, the amount of independent random variables also has to be relatively small. So in our case, if we try to use McDermott's inequality naively, what we are going to end up having is m-squared random choices. And this is because we are interested in what happens on roughly m points in time. And at those points in time, we have at most m balls. So in the worst case, we have at most m-squared balls overall. And so if we feed those m-squared random choices, so that is if we fix k to be m-squared in McDermott's inequality, what the inequality gives us is that x is at most the expectation plus O tilde of m. And here I removed the Lipschitz condition. But the important thing here is that this is too weak for us, because remember, we are shooting for O of n. Okay, so we can't just apply McDermott's inequality directly. So at a high level, the approach we take here is that we separate the balls into two groups. We're going to have the important balls and the non-important balls. So the important balls are the A1 to AM prime, right? Which are the balls we have at the end of the process at time t. And so first, we're going to fix the randomness of all unimportant balls. And we're only going to use McDermott on the randomness of this O of m important balls. And when you use McDermott's with that k, the band you get is the expectation plus square root of m, right? And so that is going to be good enough for our purposes. And then after this, we unfix the unimportant choices and we complete the analysis. And this part is also a large part of the analysis. So it's not like after you apply McDermott's, everything goes smoothly. But this is roughly what the structure of the proof is at a very, very high level. Okay, any questions? Okay.
So you don't have to deal with the actual balls into bins. You can use as a black box the existing results, right?
Well, yes, to apply McDermott, yes, you can use it as a black box. But then when you unfix the unimportant choices, you're gonna have to do a classic balls and bins analysis. Yes, it's not that. It's not only an application of results as black boxes. Okay, so with this new theorem, we're gonna construct an Iceberg hash table. Okay, so we solved this balls and bins problem because we had an application that required a dynamic unordered dictionary with the following requirements. It has a succinct representation, meaning that if you have capacity for m elements, the size of the table is 1 plus little of 1 times m words. It has constant time queries and updates. It doesn't reallocate items. And it has compact fingers. And by fingers, I mean some kind of information that lets you read or write an element in just a single lookup. And in fact, this was related to the application we had was related to address translation in a real machine. So if you want to know more about that stuff, I'm happy to talk about that offline. Okay, so there are a lot of papers about dynamic hash tables. So a fair question is, well, isn't this already solved? Well, the thing is, typically, these dictionaries optimize query and update performance, but they do this at the expense of reallocating items or allocating linear size tables. So you have a lot of papers. For instance, the very first one, it's a very famous paper by this Filbinger et al., and it does dynamic FKS. And here they don't do any reallocation, but they allocate a table that it's 35 times m words. Then you have a bunch of paper that use cuckoo hashing, or to some extent in some part of the structure, or some kind of variant of cuckoo hashing. And then you have some other papers that use graph-based allocation. And so some of these papers, some of these hash tables are optimal in query and updates, and also they are succinct, but they do this kind of reallocation, and that really hurted us in our application. And this list is not exhaustive, and I'm not saying there is no other paper that has a hash table that satisfies to some extent our requirements, but I feel it's unlikely. And also that the hash table we're going to build is really, really, really simple. Okay, so what is Iceberg hashing? Let's allocate a very large array of memory and divide it into buckets, let's say n buckets. And all of these buckets are going to have the same size b. Okay, let's suppose for now that we have already fixed n and b. And let's see what an Iceberg hash table does. So when we want to insert a new element, we're going to hash the key value item according to Iceberg 2. The buckets are the bins, and the items are going to be the balls. and the ball ID is going to be the key of the element that we're trying to insert. So we basically, at this point, we use Iceberg 2 as a black box, and we let it do its work. And when it selects a bucket, we place the item in any empty slot in that bucket. And if the bucket is full, well, we have failed, and we have to rehash all the elements. Okay. So how do we choose? Oh, and I should also say that these are insertions. You can implement queries and deletions naively, very similarly, right? You check all the 3 different buckets where Iceberg 2 can place a ball into, and you just check you scan those buckets, right? Okay, so naive implementation of all of these operations are of the size of the buckets. Okay, so how do we choose N and B? Okay, so the first goal is going to be to fit M elements with high probability. So I give you M elements. I want the table to store them without failing. Okay, so for this, we're going to pick B such that we satisfy the max load that we saw in the theorem of Iceberg D, or more specifically, Iceberg 2. And that is M over N plus log N divided by 2 times log phi of 2 plus low order terms. Okay, and so regardless of how we choose N, for every N we pick, if we choose B like this, we're going to be able to fit those elements with high probability. It's going to go through. Okay. The second goal is that we want to be succinct. And so for this, the trick is that we're going to choose N so that the dominant term in B is the average term. It's the first one, right? And so if we choose N to be M over log M times log M, so or any other thing that is slightly larger than log M, then you can see that B now it's dominated by the average. So it's 1 plus little of 1 of the average. Okay. And therefore, the number of slots we are using here is N times B. So that is 1 plus little of 1 of times M. Okay, and the fingers that we promised that they had to be compact. Well, so perhaps I should say that it's obviously trivial to get log M fingers because that's a pointer in memory. So we want to do much better than that. And here we can have much more compact fingers because to know the location of an element, we need to remember which hash function was used by Iceberg 2, right? So it has 3 and it will pick 1. So we remembered that one. And so we need 2 bits to represent that. And then we need to remember what's the offset within the bucket. And so that's going to be log B. And B is roughly log M. So what we get is that fingers are roughly log M bits. And as I mentioned, the naive implementations of the operations is O of B time. But we're going to improve that in a moment.
So do I understand correctly that the idea of a finger is that you want to have a pointer to an element that is much smaller than just log n bits?
Yes. Exactly. Okay. Yes. If you want some context, we want to fit these fingers in a cache, in a TLB. And so typically systems use fingers that are size log M in a TLB. And so we wanted to compress that a lot. And so when you have those fingers in the TLB, you want the TLB to be able to resolve the address without doing any lookups. So from those fingers, you have to figure out exactly where your element is.
But the finger is useless unless you have access to the actual element.
No, well, it's useless. If you want to read or write the element, you do need to go and read the element, right? But in order to...
You need to know what is the output of the hash functions.
Yes, that you do need to know. Yeah.
Okay.
Yeah. So yes, you definitely need to remember. Oh, I see what you're saying. Yes, you do need to remember the key.
Yes, thank you.
Absolutely, yeah. Okay. So to summarize all the guarantees, we get that Iceberg hashing satisfies that it uses 1 plus little of 1 m words of memory. It supports fingers of size 1 plus little of 1 log m bits for every sequence of operations with polynomial length where most m items are present in the dictionary at all times. It holds with high probability that it never reallocates items, and all operations run in worst case log m times log m. Right? And so here to get this high probability claim, we're just union bounding over the theorem we proved for Iceberg 2. Okay, so a couple remarks here. We can make the capacity dynamic using the classic trick of resizing when you get more than m elements or less than m over 2. And in this case, well, I guess all your bounds are going to be, your running times are going to be amortized in that case. And the other observation is that you can make all operations faster by using a per bucket dictionary that uses actually a single word. Because in each bucket you have you have log m times log m elements. And so you can build a hash table that uses poly d number of entries, and poly b is going to fit in a word which has length log m, right? And so you have a lot of freedom when you have so many little elements. So really, this is constant time. I've been a bit sketchy about how to implement that dictionary, that per bucket dictionary, so I'll have to talk about that more extensively if you want. But it's not too hard to get to constant time worst case. Okay, that's it. Thank you. Any questions?
Do you keep all of the guarantees if you make it dynamic, like when you do the resizing trick, or do you lose some constant factor?
Well, I haven't really thought this through because, as I mentioned, the real application was a different one. But what I suspect is that the operations are going to be amortized now, amortized constant. And the other thing you lose is that now you start reallocating elements.
Okay, maybe I should ask a different type of question. Can you point to a moment in your talk where it stopped being practical and it started to be a theory for the sake of theory? Because there's always this point. For example, I pretty sure believe that this fully dynamic capacity doesn't mix well with 1 plus like the succinctness.
Okay, in my opinion, so all of these papers that I cited before, they are all really very elaborate constructions. And that imposes a lot of restrictions when you want to implement those dictionaries in practice. This hash table, on the other hand, is a lot simpler. right? Because Iceberg 2 is really simple. You only need to remember a couple of counters to make your allocation decision, and then to get constant time per operation, you need to build this very, very small dictionaries. In practice, that is also very fast, because that to use those dictionaries, you're going to need a constant number of bit operations. So there's not a lot of overhead added when you go from log m to constant. And so,
but my intuition is that the last bullet point, this is actually not important. Like, this is not important in the practical setting, because in the practical setting, the bucket fits in it's already a small object that fits in a single line of cache or something like this, right? So it doesn't matter if we reduce operations inside a consecutive fragment of memory.
Yeah. Yes, you can absolutely. Yeah, you can fit log m times. Yes, you can fit that in a word. Yeah. But you do want to be able to find. You want to be able to find the right key very fast, and you don't need a lot of work to do that. It's not like you compress it, but now you need a lot of work to find the right key. Yeah. And about the resizing, in our application, we had a really, really huge hash table. So we initially allocated a very big hash table, and the thing is, you can tune the constants so that you never ever really fail.
Yeah.
So that poly-m is really large. So in practice, it's never going to happen. And if it happens, it's going to happen once. And you pay the cost of rehashing. It's going to slow down your system, but it's only going to happen once. So to answer your question, I don't feel that at any point in time I really stopped talking about a practical system. I think all of this is very practical.
Okay, but like in a practical implementation, for example, what is hidden in the small o terms would matter here. Because here you have a small o of 1, and if I understand correctly, this is like 1 over log m. That's
right, yes. Yeah. So, but for us, m is like, M is, let's say, we're talking about a full memory. So that's like 64 gigs. So I guess that's going to be 1 over what?
I'm just wondering in
something like that.
I'm just wondering in practice, what is the overhead? Is the overhead like a factor of 2 or extra 10% or
I would say it's about 10% based on the size of the M we're using. It's going to be, we didn't implement this system yet. We plan to do that. But since M is roughly 64 gigs, yes, it's going to be about 10% overhead. Yeah. But still, 10% overhead is not a lot, because in real systems, you do need 10% memory to do for instance, to pin pages or to store other kind of data that you don't want it to be handled with this hash table.
No, I mean, of course, 10% is acceptable.
So it's not that we waste 10%.
Okay, that's all of the questions from my side. I'm wondering about the other people here. Okay, I think we can stop the recording now. Thanks.
Right, thank you very much.